Hi guys, welcome back. Okay, so today I'm trying to we'll do read along, okay, and I'm trying to understand and explain to you at the same time how about LSTM, long short-term memory. It's if you heard about RNN, recurrent neural network. So this is a special form of RNN, I think. Inside the LSTM, I think there's several. It's a cell, and inside LSTM, there's several. Um, how do you say it? Several gates or several neurons. It's not just one, right? When you're talking about like neural network, right? So each individual neuron is just like transformation function, linear function, right? That just one thing, just to W uh, times x plus b, right? So input uh, multiply by the weights plus the bias and activate, right? That's all it does, one neuron. But in LSTM, long short-term memory, from what I understand, there are I think four different kind of like individual neurons that each of them like does kind of different thing. One I think one does like forgetting, the other one is does like uh, trying to remember, the other one is trying to keep, it's kind of confusing. I'm trying to understand this one. Okay, so this is suggested by the Udacity. Thank you for Udacity. So I got a scholarship from Facebook, so I'm doing it through Udacity. It's they call it, I think, PyTorch challenge. So okay, this is from the Olah's blog. It's one of the famous, probably deep learning researcher. Okay, understanding LSTM networks, recurrent neural networks. Human don't start their thinking from scratch every second. As you read this essay, you understand each word based on your understanding of previous words, right? In other words, you kind of memorize something or you recall about something, and then you understand it, and then that's how you can like uh, give a reaction or uh, feedback when people ask you, "Hey, how are you doing?" And then you say, "Oh, I'm good, thank you." But how do you know to say that words, right? Somehow in our brain we already like learn. Okay, when somebody said, "How are you?" I'm supposed to say, "I'm good, thank you." Or if that person like close to me, and then I'll just spill out my all my problems. Like, "Oh, it's not so good today. The weather sucks, blah blah blah," right? So you have this kind of rules that you remember already, right? It's there stored in your brain, right? Imagine talking like how are you to a baby or to like a 1-year-old kid. And they will just like look at you and then probably they just kind of ignore you because they don't have any like recollection. They don't have memories, right? So you don't throw everything away and start thinking from scratch again, right? So it makes me think about the beginner's view of mind, like the Zen. You're thinking from scratch, but this one is you're not thinking from scratch. You're thinking from a memory, from what had happened in the past. Your thoughts have persistence. Traditional neural networks cannot do this, which is the input plus weight, add a bias, and activate the linear transformation, right? The neural networks, the traditional. And it seems like a major shortcoming. For example, imagine you want to classify what kind of event is happening at every point in a movie. So you want to classify what kind of event is happening at every point in a movie. It's unclear how a traditional neural network could use its reasoning about previous events in the film to inform later ones. Recurrent neural networks address the issue. They're, they are networks with loops in them, allowing information to persist. So this is the input time t. Let's say t is equals to 1, right? What is this? Oh, that's cool. Okay. Goes to the this box called A, right? And then does something here, like a black box or not a black box. There's a mathematical transformation going on here. Think about this like a um, yeah, it's just a mathematical functions, right? And then spits out an output, which is hits t time t. This is still the same. If you put it at time t, the output is going to be time t. But at the same time, it also spits out an output. Now, this output and this output, I'm not sure. I think it's different. But that output is going to loop a feedback. I think this is the one that making it able to remember something, right? Because you're looping back whatever output. Say something you let's say this is you or me, right? And then somebody's talking to me. Let's say I'm like 2 years old, 3 years old. Hey Danny, how are you? Right? All those sentences. Hey, how are you? And then I process that, right? How are you? And then I'm thinking, okay, how am I supposed to answer that? Oh, I'm supposed to say I'm good. Okay, so that's the output here. And then you kind of remember that because you're saying I'm good, and then probably you can tell like, oh, what is the reaction of that person, right? If it's good, then probably you will keep it. If it's bad, then probably you throw it away, right? Depending probably on the reaction. But anyway, you have an output, and then you can loop it back. And then I think over here you can like sort of decide when to keep it or when to forget about it. Anyway, let's move on. In the above diagram, a chunk of neural networks A looks at some input xt and outputs a value hits t. A loop allows information to be passed from one step of the network to the next. So a loop allows information to be passed from one step of the network to the next. Okay, these loops makes recurrent neural networks seems kind of mysterious. However, if you think a bit more, it turns out that they aren't at all that different from a normal neural network. A recurrent neural network can be thought as a multiple copies of the same network. It's passing a message to a successor. Consider what happens if we unroll the loop. Okay, so if you unroll this thing, so mm, okay. So it's so you have start from x0, x1, x2, and then dot 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 until t, and then um, doing the same thing. So x0 at time 0, which is like you can think like you can think like probably like time 0. Let's say like 10 years ago when we're still like younger. You have an interaction with somebody, right? And then you've processed that interaction in your own brain, right? Your brain has a like a function there, and then you spits out an output, right? And then based on that output too, you put it into your brain, right? That model you can because you are like learning, right? And then at so this is like let's say 10 years ago, and then at 9 years ago you're doing the same thing. You're having an event with somebody. You're making a decision or you're talking to somebody. So that X1, that's your input to your brain, and then you process it in your brain, right? And then you spits out to that whoever is talking to you, which is H1 9 years ago, right? and but that spits out. I'm assuming this is the same, okay? This is the same. If it's different, then okay, whatever. But this is like the output, right? This is like coming out from your brain, right? The H1, the result, the output of the function of your brain, right? And that thing also goes back to your brain, and you kind of store it there, right? Like a memory. So you kind of this is I think you kind of learn from the past, right? You can think about it learning from the past. So you talk to that person at 9 years ago, and 8 years ago, you have the same thing again. You have an event. You're talking to a person. So right, you have an input there. You put it in your brain. You're thinking about it, and then you're also thinking you have, but you still recall like from 2 years ago, from Hitch now, because you put it in your brain. And from 9 years ago, the event also you put in your brain, right? So before you spits out hits two, you're considering the fact that the hitch zero occurs and H1 occurs before you spit out hits two, and then you're thinking about it, thinking about it, thinking about it, and then you spits out the hits two, right? So you give a feedback to the person who you're talking to 8 years ago, and that person probably is like happy or sad, whatever the reaction. You remember that because you're putting it back. You're putting it back to your own brain, right? Whatever reaction, whatever like results, right? You got the interaction like 8 years ago. And then the same thing happened like 7 years ago over here, like X3, right? You're having an event, and then you're putting that event into your brain, right? Interaction into your brain, and then your brain is thinking like because you have a memory from like the past 3 years. So before you even giving an output at hits three, giving a answer or response to a party or two person at hits three, you have to consider the past 3 years of your experience, right? And then you think to yourself, oh, I remember like 3 years ago, I have a not nice experience when I'm having a event like this, right? But 8 years ago, I'm having a good experience or good like response. But like, and then you think again, oh, but last year I mean having an event, the response has been great. Okay, okay. So based on that, probably I have to like give a response like this. So and so on and so forth. So yeah, okay. This makes sense. When you unroll it, it's just a thing in the past that you kind of take into consideration. It doesn't mean that it will affect, I would say, um, because inside this function, like I said, inside this recurrent neural network, there are several functions, which I think to forget, to remember, to even to select, or even to drop something. So you consider something happened in the past, um, and then you take that into consideration, and then you can like drop it, or you can like uh, put it into uh, uh, like affecting the new decision that you are making at the current uh, event, right? So the chain-like nature reveals that recurrent neural networks are intimately related to sequences and lists. Okay, they are the natural architecture of neural network to use for such data. Okay, cool. And they certainly are used. In the last few years, there have been incredible success applying recurrent neural network. What is recurrent means? I think it's looping. Recurrent. I'm just occurring often, repeatedly. Okay, so repeated neural networks are occurring often. Okay, just keep on repeating. Okay, all right. Um, where's the? Okay, here. Where are we? Okay, so and they certainly are used. In the last few years, there have been incredible success applying RNN to a variety of problem. Speech recognition to recognize a speech. So, like, I don't know if you guys have a Google Home Mini. I love Google Home Mini. My kids love it. I think we've been having it for I don't know the past like a year or two. So when you talk to Google and you say, "Hey Google, what's my name?" It will know what is my name. It's like my name. Your name is Danny. Your name is Matthew. Like at the first place, like how does it recognize that that's my voice? That's amazing. So it kind of recognize that it's you. It's not like some random people. Although, when I tweak my voice like, "Hey Google, what's my name?" You know, like a high pitch voice or like very like low bass voice. "Hey Google, what's my voice?" Then Google Home is like messed up, right? A bit messed up. But if I use my like normal like tone or whatever timbre, right, sound, it will recognize me. So it means like it has like a memory somehow, right? So I think it analyzes like my uh, when we talk, we produce like a kind of a what electromagnetic wavelength, right? And then the microphone turns that into electrical pulses basically. And then the electrical pulses from the electronic circuit, it transforms then into because it has to be digital into basically bits, right? 0 1 0 1 0 1, right? But based on that 0101, somehow the computer like knows that it's me it's talking, right? And then it knows how to respond appropriately. So for language modeling, I'm not very particular. Yeah, I'm not sure. Translation from if you use like Google Translate from English to Spanish or from Spanish to English, or from English to French, or French to English, from Japanese to English, or Japanese to Indonesian, or what have you, right? First, it has to kind of recognize what language are you speaking to, and then somehow translate that into a code, into binary, and then Google Home will know how to respond, and then have to translate that response, which is in binary in a computer code, into French language. If you're translating, let's say, from English to French, that's amazing. It's amazing. Image captioning. So image captioning, I think is the one that's if you watch like a YouTube and you want to see the subtitles, or even like Netflix, or like watching like movies. Uh, yeah, the list goes on. I'll leave discussion on the amazing feats one can achieve with RNN to Andrew Karpati excellent blog post, the unreasonable effectiveness of recurrent neural networks. But they are pretty amazing. Excellent to this success is the use of LSTMs, a very special kind of recurrent neural network which works for many tasks much more better than the standard version. So LSTM is a special kind of RNN, much better than standard version. Almost all existing results based on the recurrent neural network are achieved with them. It's this LSTM that this essay will explore. Okay, what's this? Doesn't work. For the uninformed reader like me, mentioning the full would be very helpful. Okay. Business math. Somebody regretted. Oh, dang, I knew I shouldn't have chosen business math. Okay, move on. Okay, so, okay. Okay, the problem of long-term uh, dependencies. One of the appeals of RNN, recurrent neural networks, that happens often is the idea that they might be able to connect previous information to the present task, such as using previous video frames might inform the understanding of the present frame. Okay. So using the history of the video frames might inform the understanding of the present frame. Okay. Of course, because you know what like the context, like if you're watching a movie, right? If you're watching a movie, for example, at time 30, then sometimes you will get confused because you don't understand what's going on in the movie, right? You have to go back like in the beginning or like just like 10 minutes before that to understand, okay, this guy is talking about this, he has this problem, he's trying to solve this problem. Okay, now it makes sense why he's like saying all of this stuff or why he or she is doing all this stuff, right? So you have a dependencies, but you have to go back like in time, right? If RNN could do this, they'll be extremely useful. But can they? It depends. Sometimes we only need to look at recent information to perform the present task. Okay. Yeah. If you don't need any historical data, then you don't need to remember stuff, basically, right? For example, consider a language model trying to predict the next word based on the previous one. If we are trying to predict the last word in the clouds are in the sky. Okay. We don't need any further context. It's pretty obvious the next word is going to be sky. Okay. Because if you type in this word, let's say the clouds are in the you don't need to go back in history, right, to answer this, right? Okay. Because there could be just like one answer for that, right? Where the clouds can be, right? It's always in the sky. Is it going to be like in the moon or in where my mom is belong? No, right? So okay, could be if it's like a poetry probably, right? Um, in such cases where the gap between the relevant information and the place that it's needed is small. What does it mean? The gap between the relevant information and the place that it's needed is small. RNN can learn to use the past information. Okay. So at time 0, give an input to the RNN or LSTM, what have you, and then the output goes to the to the brain. I would say like this to the cell, okay, to the RNN time x1, right, and give output h1, and then the output of that also goes to the same LSTM, so to speak. Okay, and then hits 3. Okay, so okay, so this is okay. Okay, so the input is at the in the past, and you're predicting like in the future, kind of. Hits 3. This the way I understand it. Let's see some of the comments here. What is the connection between this figure and the text? Short-term input. Okay. But there are also cases where we need more context. Consider trying to predict the last word in the text. I grew up in France. I speak fluent French. Okay, so this is like easy, right? So if this is like x0 and then x1, x2, x3, x4, whatever, right? And then this one again like x5, x6, x7, right? So you just have to go back like what, like seven in the historical data to predict what's the next word, right? It's French. Recent information suggests that the next word is probably the name of a language. But if we want to narrow down which language, we need the context of French from further back. It's entirely possible for the gap between the relevant information and the point where it is needed to become very large. It is entirely possible for the gap between the relevant information, which is here, France. This is relevant information to that you need to be able to speak. To be able to know that the answer is French, not Spanish, not Indonesian, not English, not Japanese, not other language, right? Um, to get between the relevant and the point and the point where it is needed to become very large, very large. Okay. So it's like this. The cap to answer this, you have to go back like in time to know x or x1. Okay. This one is not so. You don't have to go back a lot. Like you have to go back like one, two, three, like right, like three, like three. I don't know, three steps backwards, kind of. Right? But this one is saying that sometimes you have to go further back, right? So it's entirely possible for the gap between the relevant information and the point where it is needed to become very large. Okay. Unfortunately, as the gap grows, RNN becomes unable to learn to connect the information. So I think this one is saying that RNN doesn't have a long-term memory. The memory is just short-term, I think. Because if the gap grows, if this is widened, let's say the things that you need to go back, let's say go back way back like x0, like while you are like I don't know x1, like trying to answer the h1 million, right? Then then you there's no way to go back there because it's like gone. The data is gone, completely gone, right? Okay. In theory, RNN are absolutely capable of handling such long-term dependencies. What? Okay, in theory, but a human, but probably in practice cannot. A human could carefully pick parameters for them to solve toy problems of this form. Sadly, in practice, RNN don't seem to be able to learn them. The problem was explored in depth by Hochreiter, German, and Bengio. Okay, Bengio, he's a famous guy from Montreal University, one of the kind of deep learning, deep expert, right? Together with Geoffrey Hinton, with Andrew Kaparti, and anyway, Andrew Ang, who found some pretty fundamental reasons why it might be difficult. Thankfully, LSTM don't have this problem. LSTM networks, long short-term memory networks, usually just called. So this is just saying that RNN is only good for short-term memory, but it's not good for long-term. Because if you have to go back, it doesn't do that. But it says in theory, it could be done. So I don't understand why in practical thing it cannot be done. Probably, I don't know, because too long somehow it's like you lost them. I don't know. Anyway, we'll probably know the answer later on. So this is why um, the use of LSTM um, to solve this problem, right? Because LSTM doesn't have the problem to 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 see if the gap is growing, right? For long term. is a special kind of RNN capable of learning long-term dependencies. They were introduced by Hoch, Reiter, and Schmidt-Huber, 1997, and were refined and popularized by many people in the following work. They work tremendously well on a large variety of problems and now widely used. LSTM are explicitly designed to avoid the long-term dependency problem. Remembering information for long periods of time is practically their default behavior, not something they struggle to learn. Oh. A recurrent neural networks have the form of a chain of repeating modules of neural networks. In standard RNN, this repeating module will have a very simple structure, such as a single 10H layer. So, goes to A. The repeating module in a standard RNN contains a single layer. So there's a 10H. Okay. This is the squashing function. Okay. LSTM also have this chains like structure, but the repeating module has a different structure. Okay. So this is the repeating model. Huh. But the repeating model, instead of having a single neural network, there are four interacting in a very special way. So for RNN, it's just one. The input comes in and then just being squashed after that with a 10H. Why 10H? From what I heard, it just works. Okay, why not like ReLU or any other squashing function? It just works, and that's why that's science. They just keep on trying the different experiment, and then they just see the one that doesn't work and the one that works. Why it works, I have no idea, and I think probably I don't know. Probably some people knows why it works. I mean theoretically the answer, but from what I understand, why it works, why 10 hits is because it just works. LSTM also have this chain like structure, but the repeating model has a different structure. It's more complicated. Instead of having a single neural network layer, there are four. So if you look at this, so the X goes to this is I don't know what is this. ReLU probably or sigmoid. Looks I think it's a sigmoid. And then goes to multiplication. This is a multiplication element, right? The symbol. So if you have a matrix element-wise multiplication. This is a matrix, I think, addition-wise multiplication. And then the other one will go to another sigmoid or squashing function. Okay, I'll just call it squashing function. This is basically the non-linear thing. And then you multiply it with the one from here with a 10H. And then from there you give the output and then you plus that. Whatever coming out from here, you plus that with this guy, the matrix. So element-wise multiplication. And then that goes to output. This is complicated. And then it goes to A. Goes to the same. So this one is gonna like loop feedback here, and then this guy also gonna loop feedback here. Yeah. It's a bit complicated. It is complicated. It's amazing. The engineering, it's brilliant, brilliant. Don't worry about the details of what's going on. We'll walk through the LSTM diagram step by step later. For now, let's just try to get comfortable with the notation we'll be using. So this is a neural network layer. This is pointwise operation, factor transfer, concatenate, and then this is copy. Interesting. Okay, in the above diagram, each line carries an entire factor. So each line carries an entire factor from the output of one node to the inputs of others. The pink circle represents pointwise operation. So this is pointwise, or you can say element-wise operation, right? Like factor addition, while the yellow boxes, this guy, are learned neural network layers. Learn neural network. So this is where the learning happen. Okay. Okay. Yeah. Learn neural networks here. That's where the weights being learned. Just like the ordinary neural networks, right? I think you can think of this as like the ordinary neural networks, which is wx plus b, right? That's the ordinary neural networks with a sigmoid function. In over here is just being represented as a yellow box with the so-called the nonlinear transformation or activation function, and then with a specific activation function. I think this one is a sigmoid, this one 10 hits. Okay, okay, interesting. So you can think, so this is an LSTM layer. Think about it like if you, I'm not very good in biology, but from what I understand, if you know our cell, right? Our, our cell, or any like living cells. Inside the cell, there's a what nucleus, right? And then inside that nucleus, there's a bunch of like mechanics, complicated mechanics, right? Basically, how they're like workers about how to make like the protein or the DNA, something like that, right? And each of those workers has their own like specific how is it specific functions or a specific output what they can do, right? Because they are like functions, like workers is like a function. If you give them something, they'll give an output based on that something, right? The input, right? And each of the workers they have a special skills. So you can think of that like this. So over here there's like 4 workers. Well, you can say it's only like a 2 workers, right? Because these 3 are the same, right? It's a linear it's a neural networks with the same squashing function. The difference is how they are being utilized. Like the output of this is going through the multiplications element wise with whatever the input from here, right? While the output from here is going through multiplication wise with the input of another neural network with a different squashing function, right? And then even after that is being what's it addition point wise with the output from this guy, right? While the neural networks over here, the output of this squashing function sigmoid, it's going to be also multiplication point wise with the output from this guy, and this guy is also the output from this guy, and this guy is the output from this guy, right? So it's kind of complicated. It's amazing. It's an amazing like operation like factories inside that cell, you know. So you can imagine like there are only like two workers basically. Instead of thinking about four different cells, there are actually like two workers, right? Which is the workers of a sigmoid cell. You can call it sigmoid worker and the workers of a 10 hits. Uh, but the workers of the sigmoid, think about it, the output of that workers. So for example, if I'm the workers of sigmoid, I will give my output to three different department, right? I give it to this department over here, I give it to this department over here, right? And I give it to this department over here, right? To be to be being processed again, right? So I can think about this thing is like a machines, right? So I'm a worker here, the yellow one, right? There are two workers, and me and my friend. I am a sigmoid worker, and my friend is a 10 hits worker. But the difference is, uh, whatever input I get, right, and I work on it, the result, the present for that, the result, the output of that, I will give it to three different machines. One machine's the one over here. One machine is over here. Now I can actually, yeah, yeah, it's two different machine because this machine give the output to this machine, plus machine, right? This machine also given out. This machine it generates like two, except two inputs actually. So, and then I give my also my output to um, what do you call this? Multiplicative machines, right? So I give my output to three different machine actually, and those three different machines are it's the same machine basically. It's the same engine, does the same thing, except they are being connected differently, you know, right? Because this machine is also being connected to the 10 hits. It's also waiting for the input from my friend's worker, the 10 hits worker, right? And this machine is also besides just waiting from me, is also waiting from history of this guy, of the previous time step of the output of the of 10H, right? Um, and then the third machine is being connected also with so yeah, with the 10H machine too, with the squashing function machine. Hmm. And then it's so yeah, interesting, really interesting. Now I can understand it this better. I think that's the way. I think it's good to understand it. It's thinking about that this yellow. There's only two factory workers, and there are how many machineries? Like one, two, three, four, five. There are actually five machines, um, and but out of those five machines, there are actually only three different type of machine, which is the X machine, the plus machine, and the 10 hits machine. But each of those machines are being wired differently, right? So that's why you have to treat them differently because they are wired differently. The input and the output are being wired differently. So imagine you're just working in a factory, like Amazon factory. There's only two people, you and your friend. My name is Sigmoid, and your friend is name is 10H, right? And then I'm receiving an input, right? Um, and then my friend also receive an input. And then once I receive an input, I have to work on it, right? And once I already work on it, I basically do a neural networks transformation function onto it. And then I squash it, right? So I receive that input, and then I just like the neural network, so I multiply it with the weights, right? With the weights, and the weights first is like random, right? This is the one the learn weights, right? So I multiply that inputs, and then I incorporate a bias, which is also a learn parameters, right? And then after doing that, I squash it with a nonlinear function, okay? And then after that, I give the output to through three different machines. So I go to the first multiplicative machine, okay, and then I'll just okay here's, and I just put my whatever output I have, boom, and then I go to the second machine multiplicative machine, I I I input it to the second machine, boom, and then I walk again, right? I go to the third multiplicative machine, and then I just said okay here it is, boom, and then the machine will just do their stuff. The second multiplication machine do that, and then the third multiplication machine also do, right? And then my friend also does the same thing, except uh, he received the input, and then he got uh, the same weights. I think this is using the same weights, if I'm not mistaken. I could be wrong. Okay. Anyway, assuming now it's the same weights, right? It's the same parameters. You multiply it, and then he also plus with the bias, but he will squash it with the tanh function. No, I don't like sigmoid. I like tanh, and then I'll squash it. Boom, right? And then he only give the output to one guy though. So this guy is a lucky guy. This my friend. He only have to walk to one machine, right? Which is actually is it's the same machine as me, which is the multiplicative, the second multiplicative machine I give, right? So I'm giving to this guy, boom, and then I said to him, hey, I am so jealous with you, but how come you only walk to one machine? Well, I don't know. I got paid less probably. Whatever. Okay, whatever. So I put the machine into the second multiplicative machine. Boom, and then the guy walk over, and then my friend, and then he also uh, put his output to the same machine as me. Boom, and then the machine will somehow add. Oh, sorry, multiply. He take that input from me, and then he take that input from my friend, and then he'll just multiply it, right? And then he give the output. The machine give the output because it's connected through a wire or through Wi-Fi. He will give the output to a addition machine. Boom, and then the addition machine will just add whatever uh, being received plus the other matrix or the other factors, so to speak, if we're working the factor here. Uh, okay. Yoo-hoo. Okay. Yeah, the one I don't understand. Okay, let's carry on. In the above diagram, each line carries an entire factor from the output of one node to the input to of others. The pink circle represent point-wise operation. Okay, like factor addition, while the yellow boxes are learn neural network layers. Lines merging denote concatenation. So where's the merging line? Like oh, this one and this one. Okay, so it's merging. What is concatenate? So you just add them up side by side. So if okay, you concatenate. Okay. Yeah, you don't add it up like in a math operation wide. You just like a text, like I and B become IP, like that concatenate, I think. So if it's like 2 and 4, I think it will just 2 comma 4 instead of 2 plus 4. I think that's what concatenation. While a line forking denote its content being copied and the copy is going to different locations. So forking is like Where is forking? Oh, like this one, right? So the output of this machine is going to be going as an output at the HT and also as an input going back to the input here being copied. Okay, so actually there's only two. Yeah. Okay, we got this. We got this. And the copy is going to a different location. Okay. The core idea behind LSTM, long short-term memory. The key to LSTM is the cell state, the horizontal line running through the top of the diagram. Okay, the cell state is a kind of a conveyor belt. Ooh, conveyor belt, huh? The cell state. CT minus 1, this is CT. There's xn plus. Yeah, xn plus. It runs straight down the entire chain. Okay, with only some minor linear interaction. It's very easy for information to just flow along it unchanged. Okay. The LSTM does have the ability to remove or add information to the cell state, carefully regulated by structures called gates. Does have the ability to remove or add information to the cell state, regulated by the structure called gates. Gates are a way to optionally let information through. They are composed out of a sigmoid neural network net layer and a pointwise multiplication operation. Gates are a way to optionally let information through. They're composed out of a sigmoid neural net layer, this one, and a pointwise multiplication operation. Okay. So these are gates. This is called gates. Okay. Carefully regulated by structure, called gates. To remove or add information. Okay, so with gates. So how many gates do we have? So it's always composed of a sigmoid plus pointwise multiplication. So we have this is a gate. Or always a sigmoid multiplication. Okay. And then this is a gate. So and the function of that is to remove or add information. Okay. How does that work? How is that work to remove? I mean, I can imagine to add, because when you multiply, you're kind of like adding some information. I do not know how you remove it. Like when you, I guess when you multiply it by a variable that is, does it make it like, you know, uh, less like a fraction variable, for example, right? Okay. The sigmoid layer outputs number between 0 and 1. Oh, so I'm correct. This is sigmoid. Okay. Between 0 and 1. While the 10 hex, I think, is between -1 and 1. Describing how much of each component should be let through. A value of 0 means let nothing through, while a value of 1 means let everything through. Okay. Okay. Um, an LSTM has 3 of these gates to protect and control the cell state. Yeah. So you got it 1 here, right? Sigmoid and multiplicative pointwise, and then 2 here, and then the third one is here. This is cool. This worker is amazing because it has a three contributions, sort of, which is to remove and add information to the cell state. Okay, to protect and control the cell state. What is a cell state? I'm not really sure. Okay, step by step. Is this still far? Wait, I hope we can like finish this. Step by step LSTM walkthrough. The first step in our LSTM is to decide what information we are going to throw away. Okay, we want to forget, right? Probably from the cell state. This decision is made by a sigmoid layer called the forget get layer. It looks at ht minus 1 and xt and outputs a number between 0 and 1 for each number in the cell state ct minus 1. 1 represent completely keep this, while 0 represent completely get rid of this. Okay. Oh wow, that's how it works. Okay. So you multiply it. Okay. Let's go back to our example of a language model trying to predict the next word based on all the previous one. In such a problem, the cell state might include the gender of the present subject so that the current pronouns can be used. When we see a new subject, we want to forget the gender of the old subject. Okay, I'm gonna take a break here. I'm gonna just stop here and continue.